Hello, welcome back. So in the last session, I was trying to build a distributed dash scheduler. So whoever is new to this series, welcome. Uh, this is a short series. I'm trying to get in touch with C++ and systems programming. I don't usually do this at work, but I want to kind of experiment and get to know more and do more hands-on small projects around systems and low level systems. And C++ is a language that I'm familiar with, that I've used a bit in the past. And yeah, I just want to build small things and try my hand at these projects. In the last video, I started building a task scheduler, and I implemented a simple task scheduler which used one worker and kind of it used a queue that, and the single worker would kind of ping and uh, execute the jobs that were queued in the scheduler. I actually tried recording the distributed part of this, but somehow my recording setup uh, did not work throughout the video, and my screen was frozen. So I'm just re-recording um, a walkthrough of this code that I wrote, and then I can continue on adding more features to this. Just making sure I can still see this. Yeah. So what I updated from the last session is that now instead of a single worker, I have a vector of workers. So it's a set of workers that work together to execute the jobs included in the queue. I instantiate n threads that the user of the scheduler can pass as an argument, and most of the rest of the implementation is the same. The wait until done, all done function now waits for all the workers, and essentially um, it waits until all the workers are done, and then it exits the program. There's the major change is in the do work method. What happens is now, since I want multiple threads working, kind of checking for jobs in the queue and executing them, uh, uh, what will not change is that still, like even in this implementation, all the workers would still run the do work method, but we would have to implement some sort of a locking mechanism um, because all of the workers will be working on a single queue, and we want to avoid conditions where multiple threads access or modify the queue and they see incorrect representation of the data structure. So for example, what in the previous implementation I had something like while q.size, you would pull the first element out and then you would execute it. Now, the problem with that is that you're first reading the size of the queue and then modifying it by taking out the first element and then executing it. This would be a problem with multi-threaded scheduler because uh, you might read a queue at a particular point in time, but then when you move to the point when you have to pull the element, the size of the queue might have changed because some other thread would have already executed the removal of the front element, and this might lead to yeah like race conditions and segmentation faults. So to avoid this, we need to ensure that the queue is accessible by a single thread at any point of time. And what that means is modification to the queue can be done only by a single thread. So I added a lock guard. So lock guards in C++ are essentially block scoped locking mechanisms. So they lock a mutex, or they acquire a lock on the mutex when the scope starts, and when the scope ends, they automatically unlock it. So essentially, for this piece of code, the lock will be acquired on the mutex, on the queue mutex. So I get the size of the queue. If the size is greater than 0, then I remove the first element and then kind of execute the job if the element was actually there in the first place. And this happens over and over again. So in the end, all the workers kind of keep checking for new work, and then they execute new work as soon as possible. Now to test this, I also added few new job schedules. So yeah, so the scheduler creates 4 threads, and to test this, I have 7 jobs that will be scheduled, and the job two, similar to last example, has a sleep of 2 seconds. So what we should see ideally here is that all the job one, the first jobs should like all the job one instances should execute immediately, and the job two instances should be scheduled by whichever thread that is free, and then we should see all the job two instances execute in parallel or concurrently. On the right, you can see already, like I had tested this, but I just want to show you quickly how this works. So compile it and running this. So you see the 4 hello 1 jobs are executed immediately. Then all the 3 hello 2 jobs are executed together. And this will keep on happening as many times as possible. So maybe we could even add a for loop here and it would just work the same. So in the last bit, when I was recording this, I was trying to kind of add an additional case here where I would schedule a job after a certain time, but the last time I tried this led to a sec fault. I still need to check what can be improved here. But one other important thing that I wanted to focus on is like the do work function. So currently, what is happening here is that there's a while loop that kind of the do work method depends on a while loop to keep checking for new work. But this is really we are doing a lot of work here when it's not really needed. I mean, this is a general practice. Even things like HTTP server, uh, they work in this way. They are a while loop in the end. But we could also make it a bit more cleaner and simpler in terms of execution by having a more event driven mechanism. So essentially, instead of just checking continuously if there are new jobs, what we could do is whenever a new job gets added to the queue, we could somehow notify the workers that there is a new job available. Now, this is more like a push approach. So here we are trying to implement the pull approach where the workers continuously keep on checking, but we can try to implement an approach where when a new job gets added, the workers are let known. Um, Before that, I just realized there is a small missing piece here. So when we call the schedule method, when someone calls the schedule method and the job actually gets enqueued in the scheduler queue, this also has to be protected with a lock because we are modifying the queue. Um, so I would just simply create a log guard here of type mutex. Yeah. So just to ensure that this works. Okay, it still works. Cool. Now, to implement the notification, there I know that there is a construct called condition variables, and condition variables are can be used to notify a to kind of notify when a certain value changes. So I can so a condition variable is a synchronization primitive to block one or more threads until another thread both modifies a shared variable and notifies the condition variable. So essentially, it's a way to communicate between two threads, um, but the way like we can implement it in a way such that um, we don't have a while loop in our code. So let's try to do this. So define a condition variable. We have a mutex, and so we modify the queue and then we notify. And then we wait here for the lock until return ready. Okay. So what we could do here is, let's say we define a new condition variable. I think we'll have to include a condition variable. And let's start from the point where we push to the queue. So we do something like this. We put this into a scope. And then we do cv dot notify one. Essentially, what we're doing is we are using the condition variable to notify one of the listeners, whoever is kind of watching this condition variable. And whenever we push a new job to the queue, we notify one of the listeners. Usually, it's the next one uh, that is listening. And now we will actually listen to this. So we'll remove the while one from here. I think would we be enough? Would it be enough to just use condition? Because I think this will only happen once. If we still want to, run the scheduler after it has processed or ran one job, we would still need the while loop. It's true. let's try to think about this. So file one would actually ensure that the jobs can be processed even after thread is done executing one job. Okay. So yeah. So what we are really solving is this part. So instead of kind of executing this over and over again, we would wait here. So okay. So what's a unique lock? Is it general purpose matrix ownership wrapper, allowing deafening locking, time constraint attempts, locking, cursor locking? Okay, I mean I can just use a murex here. Sorry, a lock guard here. So I can keep this the same, and then I could do something like I would wait for the CV here, and um, q dot size. Okay, I think I need to pass this inside. CV dot wait. Let's check the method definition for this. So wait takes a unique lock and a predicate. Okay, so I really have to make it a unique lock. So std unique lock. Okay, so this should acquire the lock, and does the unique lock differing lock ownership? I just want to know what is the difference between a unique lock and lock guard. Offers more flexibility than lock guard. It provides features like manual locking and unlocking, deferred locking. Okay. So place sort of actual type of the mutex. This is optional parameter. Log multiple times. Okay, let's try. So okay, so generally this should work now. So it should wait until the lock. Yeah, it should wait until there is someone who is creating a notification does not notify. Essentially here. Let's try to compile this. Okay, class requires a template argument. Unique lock should, I think, request template arguments. Okay, I need to pass mutex. Okay. Okay. Now, the difference from the last program here would be that this while loop will not keep on running. So the thread would come and stop here, versus in the previous approach, we would execute this, we would check that the length is not greater than 0 in case the queue is empty. We'll go back and then just keep doing that until there's a new job in the queue. In this case, it will come here, it will wait. So it will not kind of execute all of this. You can consider this as like a local while loop. So it will just wait here until this condition passes. So we have passed a condition that we want the queue size to be greater than 0. If it is not, then it will just wait here. And it works. Let's try the case where we wanted to add some jobs after a few seconds. Last time I tried to compile, or last time I tried to run this, it failed. Okay, this time it works. Amazing. So you can see what's happening here. Um, the first 7 jobs were scheduled one after the other. Then we paused for 4 seconds, and then we scheduled 2 new jobs, and they were also executed later because some like we scheduled them, and then some thread picked them up. Yeah, so it actually works well. Let's try a few more cases. Let's try to uh, overload it a bit. So let's try to create like 5 and 13. So 13 jobs together, and then let's see how it works. Okay, all the 1 jobs are scheduled now. Okay. Yeah. So you see this. So it first executed 1 jobs, like, and then it took the next job. I think it printed 5 hello ones because I would assume we have 4 workers, and 2 of them were busy with job 2, so we only had 2 free workers for 1. So they immediately executed 6 of them, and then they waited, and then so on. Yeah, so it works well, I think, um, overall. And we can obviously increase the pool size that we have. Let's say we have 10. Now this should be much faster than the 4 jobs that we had. So let's say, Yeah, so now we have like in total about 13 and for 17 jobs in total. But with 10 threads, it should be much faster than just four. Yeah, let's try to remove the sleep and just test seven, 17 jobs together, scheduled on 10 threads. Okay, amazing. So all the ones completed first, and then all the twos completed after that. Now, if I reduce this to four, you'd see a pattern like it will execute in batches of four. Yeah, obviously six, like six. Yeah. Okay, so this works well. We have a version of distributor, or more of multi-threaded scheduler that can execute tasks that are scheduled on a queue. I think in the next session, what I want to try is to introduce some sort of priority in this whole process. So right now, jobs are executed in a FIFO fashion. So the first job is executed the first, last one executed last. But I want to introduce some priority. Like the jobs can specify that this particular piece of work is more important than something that is already scheduled. It would be an interesting piece to add. I can already think of some ways to do this. Uh, Things like priority queues, and yeah, that's what I'll explore in the next one. See you in the next one then.